All right. Good afternoon, everyone. As you heard, my name is Kevin Huck, and I'm going to be presenting this talk on ZeroSum, which is a tool we developed for user space monitoring of resource utilization and contention on heterogeneous HPC systems, just like it says on the box. So let me get started. Let's see. I need to choose the right window. All right. So who am I? Some of you know me already. I know Marcus, for example. I've been working in the HPC space since about 2003, mostly working for Department of Energy grants, and also work on tools like Tau and Apex and this tool, ZeroSum, and related technologies around these things. So how did this project start? In April 2 years ago, I was invited to a Dogstool seminar on HPC analytics and holistic monitoring. And most of the attendees were coming from a system administrator or facilities type background. And so their focus was on how do they keep the system up and available for users. So I sort of came into it as a user myself and sort of had the opinion that, so my talk was going to be sort of representing the user perspective on performance, on just system monitoring for HPC applications. Thinking about the reasons why users monitor, how do they monitor, and what do they want to monitor, and what is lacking in getting telemetry data from an HPC application that's running on an allocation on an HPC system that you have very little control over. And sort of I wanted to advocate for the user space in this meeting, and the meeting itself and the discussions around it, we sort of generated the ideas for this tool called ZeroSum. So since my background is in performance analysis tools, the types of things that we look at are, we take an application and we're looking for opportunities to optimize the application on a given system. And we roughly have 3 different classes of optimizations that we find with applications. The first of which is we might do an algorithmic replacement. We might swap out a library or a different solver or something to this effect. And that could involve a lot of difficult code changes, new dependencies, or major rewrites. Other cases where we might just do code optimization, where we're just looking at improving the performance of a specific loop or algorithm or something to that effect. And then finally, what we run into very frequently and more often than we care to admit is we realize that the user wasn't using a optimized launch configuration. This is something that's easy to fix, but it has a high embarrassment potential because you have a user that realizes they've been wasting allocation time to this point, or maybe even publishing results based on previous runs. And these types of things can happen from misconfigurations, making assumptions about another system that don't apply to the current system, or changes to the system policies or defaults on a given system. So we wanted to address this need. And so the goal was, can we think of a tool that would help us when we're porting an application to a new system, or trying to understand how a new launch configuration or a new data set might change our behavior. Okay. So our motivation, let's think a little bit more about why users want to monitor at runtime. So one reason that they may want to monitor is for sanity check. And this is what most application developers do. They have some kind of logging that comes out of their application that lets them know that, yes, it's making progress. Maybe you print something out after every iteration boundary or something like that. And they just want to confirm that, if they've set up a job that's going to run for 4 or 10 hours or 2 days, they want to make sure that it's configured correctly and running. They want to check for misconfigurations, and they want to check for efficient utilization. So maybe you do a few test runs and you want to confirm that you're actually using all the resources in the machine in the way that you expect that you're doing it. Another reason you might want to do it is to confirm that the hardware and operating system are behaving the way you expect them to, that you're getting the types of behavior that you want, and that you can identify any causes of failure within your software. So for example, deadlocks or crashes or stalls. And we'll talk about some of those cases here later in the talk. And one thing you might want to do, which we haven't really implemented yet, is you might want to do some adaptation or computational steering. You can't, because most batch systems that launch jobs on HPC systems don't provide a lot of elasticity. You can't do things like grow or shrink your application, but you might be able to rearrange the way that you've configured your application on the allocation you've been given. We're not going to try to identify system failures. That's something that's out of scope. Although what we found is this tool was useful in helping to find some bugs in system software. And we also want to, basically what we want to do is do some debugging or correctness or validation. So we're not doing detailed performance analysis of applications with this tool. We're really just confirming that we're effectively utilizing the hardware that we've been given. So what could possibly go wrong with when we go to schedule our jobs on HPC systems? All kinds of things can go wrong, right? So, and we've seen many of these different things. So you have process placement issues where you have logical and physical mappings, how you're assigning your resources to each process, whether or not there are reserved cores for the system, how the GPUs are mapped to different processes, where the processes are going to be mapped on the node, and are you getting the best locality out of that? Typically, Slurm or other job launch software will do the correct mapping, but what you'll see is sometimes it doesn't. And so we also want to think about things like thread placement. Are we pinning to the right sockets, to the right NUMA domains, to the right cores, or are we pinning to threads, our hardware threads? Are we undersubscribing? So if we're just leaving large pieces of nodes unused, that's just wasted energy, wasted hardware, possibly wasted time where we could have executed with more threads or packed more into a given compute node. And sometimes undersubscribing can provide better performance in some situations. So some memory bound codes or other resource bound codes. But what we find is that, typically running with a thread on every hardware thread, an operating system on every hardware thread can provide good performance benefits. And of course, you don't want to oversubscribe where you're increasing contention with no realized benefit, and actually you can make the application run slower if you're oversubscribing on a node. You may also want to look at things like imbalances. So if you have communication frequency or volume between pairwise MPI ranks that are on different nodes or different racks, you want to take that into consideration. Maybe you could do some logical mappings with your MPI to get better locality for your communication. And the big takeaway here is that Slurm, PBS, ALPS, Torque, Flux, all of these different launch systems are complicated to use, especially when you combine environment variables associated with MPI, OpenMP, GPUs, or even other model settings. Like if you have asynchronous tasking runtimes that are doing their own process binding and thread binding, then you could run into issues. So although we have documentation for these different systems, and sometimes the documentation can be accurate, usually it is accurate, but it can also be confusing or misleading. So on the left, we have a now obsolete system, the Summit system from Oak Ridge National Lab, which is based on IBM Power 9 and NVIDIA V100s. And if you look at a node like this, if you're a naive user and you're not careful, you may not notice that the last core on the first socket is core 83, but the first core on the second socket is core 88. And the reason for that is because there's another 4 cores that are being used for system utilization, so they're part of the core indexing, but they aren't actually part of the 2 sockets that the user is allowed to use. So if you're naively mapping processes to cores and giving Slurm, or I guess in this case it would be JS run instructions for where you want to pin threads, you can easily pin to the wrong cores or to the wrong hardware threads. And so in this case, we have 168 hardware threads, but actually they index all the way up to 171. So you really have to read the fine print on the documentation to understand what's happening there. And then on the right, we have a frontier node. And this is a similar architecture to what the Lumi nodes are at CSC in Finland. And the same architecture, same system. And in this case, we have the first NUMA domain has the first two L3 cache regions that actually map to GPUs 4 and 5 instead of GPU 0. And this can be confusing for a lot of users, especially if you only launch one process per node and you only ask for one GPU, it's going to be mapped to cores 48 through 55 in that first, in that last NUMA domain, that the first L3 cache region of the last NUMA domain, this one that's down at the bottom. And so essentially the takeaway is that, core indexing and hardware thread indexing and GPU mapping is not universal and sometimes not even intuitive. And so this can get even more complicated when after the Frontier system was up and running, they changed the system defaults and they reserved 8 cores per node for system resources. And this is user controllable. You can ask that it not reserve these cores, or you can tell it how many cores you want reserved for system processes. But you need to be aware that now your processes are going to be mapped on only 7 cores out of 8 for each different L3 cache region. And if we look at some other system architectures, for example, Perlmutter, which is a NVIDIA GPU-based system, we have a node diagram, but we have no information about indexing or which cores are physically closer to the GPUs and so forth. And then on the right-hand side, we have an Aurora node, which is an Intel PVC Ponte Vecchio GPUs, as well as Intel Xeon processors. And again, we have no information about core layout or GPU indexing or anything like that. So we can get this information from tools like HWLoc, and that's actually a library that we utilize in order to do this correctly. And so trying to understand how jobs are mapped to nodes, we started this project called ZeroSum, and it's for user space monitoring of resource utilization and contention. And it was inspired by a utility called Hello JSub from Tom Papatheodore at Oak Ridge National Lab. And what that was is just a simple program that would launch an OpenMP loop, and every thread would report which core it was assigned to. You would also report which GPUs you bound to and so forth, or at least the bus ID, so you knew which GPUs you were assigned. But we wanted to be able to use that same functionality within an actual application. So not just a OpenMP application. But I mean, there's problems with just running an OpenMP loop. That's just a parallel region. It turns out if you do things like use teams or target offload, you're actually going to get very different thread mappings than you would from just a parallel region that you launch from a simple program. So why did we name it ZeroSum? Well, this is it's a term from economics where an advantage for one side usually results in definitely results in an equivalent loss for the other. And this is in reference to the fact that we have a fixed number of resources available in an allocation. So we have no elasticity within a single node or even within our allocation. And we have the need to periodically use some resources to monitor. So we're going to rob a little bit from our application to monitor, but what we'll see is that the overhead is very minimal. The software is available on GitHub. And what it does is it monitors application threads, the hardware, memory, and GPU hardware for all processes, all nodes within the application or within the allocation. And this was first presented as a workshop paper at Supercomputing 23, and it's been evolving since. So what is the functionality? The type of things that we're trying to accomplish, we're detecting the initial or changing configuration of the application. We are evaluating the configuration to automatically detect misconfigurations. The automatically is not yet happening, but we can detect misconfiguration by looking at the data that we collect. We'd like to provide runtime feedback to the user that the program is progressing. So we have heartbeat type output if desired. At the end of execution, we provide a report for how effectively the hardware was utilized. And we provide a report of how much contention was identified in the execution. And we also want to be able to provide a way to expose the observed data to other tools that can perform computational steering or runtime optimization or reconfiguration. One other thing that's not listed on this is we actually also provide a way for performance tools to combine with ZeroSum. And so the types of measurements that ZeroSum are doing could be passed on to another tool like Tau or SCORP or Apex or other tools as well. So the way you use it is you launch a wrapper script in between your srun command or your MPI run and your application name, very similar to other tools. And it's a wrapper script that will set some environment variables, preload the ZeroSum library, and then launch the execution or launch the application. You can specify the periodicity for how frequently you want to monitor data. The default is once per second. You can set that to much less frequently or more frequently if you like. You can have detailed or verbose output, helpful for debugging. You can provide a memory heartbeat to just let you know how much free memory is available on the node after, on a periodic basis. You can register a signal handler to handle crashes or any other types of signals that happen. You can run the application in a debugger, and we'll see an example of this later, where you can also specify the debugger you want to use. And so in this case, you have various vendor-specific implementations of GDB that we can script GDB and run the application inside of a debugger at scale. So thousands of ranks all running in GDB if you're trying to capture a crash or a deadlock. We do deadlock detection because we're monitoring all the threads and the processes. We can do deadlock detection, both live deadlock and true deadlock. You can set a period of how long you expect, how long you think inactivity is considered deadlock. And you can specify the core that you would like to pin. So ZeroSum is doing all this with an asynchronous thread. You can specify which core you'd like that thread to execute on. So you can move it somewhere that you know that your application will use have less need for that core. And as I mentioned before, what this script does is it preloads the library, which has a wrapper around libc start main, or on some architectures creates a global static constructor destructor functions to set up ZeroSum. So internally, what it's doing is it's querying the /proc file system. And there's no great mystery. This is data that's been available in Unix style systems for decades. And we're querying the process, the self or the process ID status to get all the allowable cores for a given process. So with MPI run or srun, the process is bound to a certain number of cores. We query status to figure out which cores those are. We query proc-mem-info to get the total memory available and the memory available on the node. So that's a node-wise measurement. After MPI initialized returns true, so we're not wrapping MPI initialization or finalization. We're just checking to make sure that MPI is ready to go. And then we query the MPI rank, size, and host name. We can also do this with environment variables. So we don't have to do this through the MPI API. We can actually just query environment variables that are set by Slurm or Cray or other the PBS, so that we don't have to actually interact with MPI if we don't want to. And that allows you to run ZeroSum with other tools that are interacting with MPI, for example, Darshan or SCORP or Tau or so forth. If it's available, and it's usually, and since we've integrated HWLoc, it's turned out to be very useful. And so we recommend configuring ZeroSum with HWLoc. We're querying the hardware topology and getting every property for every node along the topology, similar to what you would see out of LS-Topo, but with much more detail. So we're querying everything that HWLoc is allowing us to see. We are querying, we launch an asynchronous background thread at initialization, and it periodically queries the process status to get the thread count and memory usage. We also query the task directory to get all of the thread IDs. So we're not wrapping pthread create. So because there are ways to launch threads that don't involve calling pthread create or don't involve, well, it's going to involve pthread create. But if you're trying to wrap pthread create, there are libraries that link a static version of pthread create or call pthread create from a DLSim call. So there's lots of ways to hide the fact that you're launching threads. But from the operating system perspective, it knows how many threads every process is running. And so if you query this directory, you can get a list of all the active threads. And then for each thread that we find, we are querying the affinity list for that thread, and it may change over time. The utilization for that thread, the state, the core it's running on, context switches, and other metrics. And we'll see some of those examples. And then we query process or procstat to query the core utilization of the cores, both the cores that are assigned to our process and optionally all the cores on our system, so that we can see if there's any other contention on the system. If configured with this support, we use the OpenMP tools interface callback to identify OpenMP threads when they're launched. That's just for annotation purposes. It's not necessarily to know that they're there. It's just know that this is an OpenMP thread versus just a generic P thread. We also use NVML, ROCm-SMI, or SYCL libraries to query GPUs and query their status. So if you've run NVIDIA SMI or ROCm-SMI on just a simple compute node, you can see the state of the GPUs. We're basically using that in a distributed system using the libraries, and so we can query utilization of all the GPUs in a run. And recently, we also added support for Cray power energy counters. So for systems like Lumi, we can query the energy consumption for various levels within the hardware architecture. At the end of execution, we write out a utilization report, and rank 0 is going to write out a report to the screen for its data. We're going to write out a report to a log file, including all the time series data as CSV data. And we write out all the observed threads. We write out all the observed cores. All the assigned GPU stats are reported, and we write out the HWLOC hierarchy as a JSON file. And then with post-processing, we combine the JSON data with the CSV data and generate a sunburst, which we'll see some examples of that. And we can generate time series charts of performance data as well. So what the report looks like is something like this, where we report the duration of execution. We have a process summary. This is just from process 0. So we see which node it ran on, which CPUs it was allowed to run on. And then we see all the lightweight processes or operating system threads within that process, and where they were running and how much system time, user time, non-voluntary context switches and voluntary context switches it experienced. In this case, we see that there's a high number of voluntary context switches because this is an application that was doing OpenMP target offload, and there was a lot of yielding to the operating system every time that a kernel was launched or data was transferred. We also report the CPUs, the data for the CPUs that were assigned. We see that there were 7 cores assigned to this process. We only used 4 of them. 3 of them were left idle. And then we see the GPU, a summary of the GPU data that we saw for this process, where we see the min, mean, and max of various metrics that we collected throughout the run, including things like power, memory activity, and overall utilization. So I talked a bit about contention detection. We have voluntary and non-voluntary context switches. We capture minor and major page faults. We capture how much time was spent in system time, which is typically when you're trying to do locks or mutexes or semaphores, or also any other system call. We compare affinity lists across threads and across processes, or we'd like to. So a lot of these are to-do items. Manually, we can do this stuff, but obviously we would like to be able to do this automated. Would we capture the memory consumption, the GPU memory consumption? And the question is whether we can do this analysis with reinforcement learning or some other form of AI, or if we can just use heuristics and keep it simple. And so I mentioned we can also, because we're capturing all this data, we can detect deadlocks, both active and passive. So here's an example from the paper that I mentioned earlier in the talk. On the left-hand side, we have a naive launch using srun, where we say we're running 8 processes, running the mini QMC app, which is ECP proxy application from the exascale computing project. This is an MPI plus OpenMP version of mini QMC running on Frontier. I'm running 7 threads. And what you see on the left-hand side is the system time for the various processes is very high. I'm sorry, you don't see the system time. You see the user time is split because all of the threads were pinned to just one core. And we see a lot of non-voluntary context switches, which is just the operating system swapping our threads in and out in order to try to time share on one core. So this is a very bad performance. So the user realizes, okay, I should have added the -C7 to indicate how many cores I wanted to use per process. And so then if we say, okay, give me 7 threads per core, then we get 7 cores assigned to our process. We get much better performance. We get higher utilization from the user time, but we're also seeing some context switches happening still. And that's because we didn't do any process binding. And so if we use the OpenMP environment variables to do a process bind spread and assign to cores, then we see our non-voluntary context switches almost disappear, with the exception of the last OpenMP thread, because it's sharing a core with our ZeroSum thread, which is doing our periodic measurements. And so we can see that the tool is helping us to confirm that we're actually getting good utilization out of the node. As far as overhead, when we're running just 1 thread per core, the overhead is negligible, if 0. And actually, the test that I ran, the application ran faster with the tool. It's probably just an anomaly. But you see there's a lot more variability between runs. And so this is a case where I ran the application 10 times and looked at the different runs to confirm how much overhead we're seeing with and without ZeroSum. And if the application is using all the cores on a node, then we do see some overhead of about 0.5%, where the last core, where the ZeroSum thread is executing, is sharing a core with, or sharing a hardware thread with one of the application threads. As I mentioned, we can do time series analysis. So if we grab some of the time series data for GPUs, in this case, this is an application called XGC, which is a fusion simulation application running on Frontier. This is 64 MPI ranks, so a fairly small job. We can see the data averaged across all the different processes. So this is 64 processes worth of data. We see when the device is busy. We see this application is very bursty. Not all of the kernels have been ported to GPU. So we do some execution on the GPU, and then we do some execution on the CPU. Once we've passed the initial warm-up stages of the application. Here, we're only running for 10 time steps, and so we're seeing 10 time steps with some iterations as well. We can see when the memory is busy for the GPUs. We see the energy consumption, and we see the variability in temperature measurements between the different GPUs based on where they're located within the node and within a rack. And then we also see some voltage variability between different GPUs. And with this data, you could also see if you could do some correlation between perhaps the performance related to energy consumption variability or temperature variability and the performance of processes. We're not doing that analysis, but you could potentially do it. Looking at the CPU threads, so on the top, what we see is all of the hardware threads from all the ranks. And so this is 896 hardware threads. And we're looking at the hardware thread utilization. And in this case, what we see is when we look at all of the hardware threads, we're very underutilized. We're only using about 10% of the node. And that's because we're iterating between OpenMP loops and offloading to the GPU. And so that's not unexpected. And so we see that we have high idle periods when we're not doing OpenMP loops. If we look at just the main thread and compare the main threads from all the processes across ranks, then we actually see some interesting comparisons. We see that some of the ranks actually have large dips in utilization. And then we see at the end of execution, we have a large period of time where we're doing file IO as well. So we also capture a little bit of MPI-PP data. This is a type of analysis that actually is done much better by other tools like Cube or SCORP or Scalaska, but you can get a map of your communication matrix between different nodes. But since we're capturing this data, or potentially capturing this data, we could also put that data into a peer-to-peer graph of some sort. That might be interesting as a form of post-processing analysis. In addition to this heat map of communication frequency and volume between different MPI ranks, there might be other ways to present this data that could be more interesting. So some successful use cases we've had with this tool. We've used it with the OctoTiger HPX application, examining thread placement on Fugaku. It turns out the Fugaku, not unlike Summit, has some unusual core mapping. And so just doing naive core mapping, thread mapping to cores was incorrect. And so you actually need to increment by 12 because there's a weird offset of 12 cores going on in that machine. And so you need to use HWLOC to confirm where your logical indexes are for all the different user cores. We used it with Argobots to confirm that, to find out what a strange contention was between a client and server. We looked at a lattice QCD library on Frontier to confirm and find ideal resource mapping for custom bind arguments. And then finally, we also, because I work a lot with the XGC application, we had a couple cases where we were doing deadlock detection, both to find a libfabric or MPI implementation bug on Frontier, but then also to find an algorithmic deadlock in MPI on Perlmutter, which is another system at NERSC in the US. So let's talk a little bit about the deadlock detection. So what this does is it runs the application in either GDB or some vendor variant of GDB. And the sequence of commands are scripted. So it'll preload the ZeroSum library, it'll load the application, run the application. If the application crashes, then it will generate a backtrace. And it writes all this data out to individual logs for each rank. So every rank is writing out a GDB log. If all of the threads are sleeping for some number of seconds, which is user configurable, then ZeroSum will call pthread kill on the main thread, which will transfer control over to GDB, which will do the backtrace, and then we can post-process the backtrace, which we'll see an example of. If all of the threads except for one are sleeping, and that thread doesn't have at least one minor page fault during that time, it's probably deadlocked at an MPI collective. And the intuition here is we were looking at the data of how we might determine a deadlock within an MPI application. And what we found was when you're stuck at a deadlock in MPI, your main thread is just constantly checking the network interface to see if there's a message waiting. And so it doesn't look like deadlock because it's got a high IPC. But you're actually spinning in just one location. You're not touching any memory that hasn't been allocated or freed. And so the heuristic basically just tells us that the application is deadlocked. And so GDB will intercept the signal and, as I mentioned before, generate the backtrace, and then we post-process it. So this is very similar to what the stat tool or CRAY-STAT tool does on some systems. The big difference here is you don't have to actually log into a allocated node and tell the node to generate a call stack or a backtrace. It'll do it automatically when it detects the deadlock in that case. So let's say we've got a case. So this is again the XGC application. It was deadlocking on Perlmutter. Let's see if I go back to remind you about this use case. We were running on Perlmutter. The queue times were around 8 hours. And so the user wasn't able to babysit the Slurm request and wait for it to deadlock. And so this tool enabled us to just launch it and let it collect the deadlock backtrace. So by looking at the backtrace, so this is a stack backtrace for all 512 ranks merged into one tree. And the color indicates how many ranks are going down different paths of the overall call path. And if we zoom in a little bit, we can see that there's a main place where most of the ranks are off on one side, and there's a handful of ranks that are off doing something different. And if we zoom in, then what we see is that we have 52 ranks that are stuck at an PMPI allgather, and that should have been 64 ranks. And the reason this deadlock happened is because this was a very obscure corner case that happened after a checkpoint was loaded, after some tens of thousands of iterations. And there was an optimization added to the code that said, well, if I don't have anything to communicate, then I just bypass this, this data exchange. Well, the problem with that is that rank was still part of that collective, still part of that communicator used for that collective. And because it didn't participate in the collective, the other ranks that were participating in the collective deadlocked, waiting for everyone to communicate. So we were able to find this bug and fix it in the code, and that was very helpful. So talking about the HWLOC data, let's see, I've got maybe a few minutes left. The HTML output that we generate allows us to provide a user interface for the user without having to install a user interface. And so we're just using an HTML template with JSON and CSV data, and we're populating an SVG object within an HTML page, and it allows us to interact with this data. So we can see where our processes are mapped within a node. This is an example of an Aurora node. And so in this case, we have 2 different sockets that each have a shared L3 cache across both sockets. We can see all the different PCI devices within each package. We can see you can't really see it well from this perspective, but you can see the NUMA domains or the memory regions. We can see network devices, IO devices, and so forth. We also see the GPUs, which are separated into different tiles on this particular architecture, and we can see which processes are mapped to which tiles based on the HWLOC data. And on the left-hand side, you see the metadata as well as performance data we collected for a given resource. For example, in this case, it's a GPU tile. And this visualization was inspired by the MEMAxes tool, which was a tool from Lawrence Livermore about 10 years ago, which was looking at memory locality within a single node. So here's an example of a run that ran on Frontier. This was 64 ranks, 8 nodes on Frontier. And so you see this is somewhat scalable in that we can show 64 different ranks executing on a job. And so we can zoom into one machine. We see the 8 processes for that one node. And we zoom into one group and we see the 2 different L3 cache regions. We see the 2 different GPUs that were assigned to each of the ranks. We can see the utilization statistics for the different threads and the different GPUs, as well as metadata that we get from HWLOC for these different members of the hierarchy. And using this tool, we can see how the processes were mapped across our job. And this also helped us to identify a bug in Slurm that I reported to OLCF at Oak Ridge. So we were comparing threads per core equals 2 and threads per core equals 1. And on the right-hand side, we see the mapping that we expect, where we have 1 thread per core, and we see that it's pinned to a specific hardware thread per core. And we are assigned to the GPUs that we also were expecting. So we get good locality for our GPUs. And what's hard to see is that the GPUs are part of the PCI bridge for each of these different L3 cache regions. And so you see that your process was mapped to the right GPU if we could zoom in a little bit further. But on the left-hand side, what we see is even though we used the GPU bind equals closest, if we say threads per core equals 2, then Slurm is going to pack our processes in to these various L3 cache regions. And then the 8th MPI process per rank is going to be spread over all 8 L3 cache regions. And the GPU it was assigned is over here on the left in another L3 cache region where none of the threads were pinned. And so what we see here is we're going to get very bad performance out of our allocation simply because we didn't bind our processes to the right hardware. So as conclusions, this tool helps us address the configuration optimization problem. We don't have any automated misconfiguration or contention analysis. It would be nice to do. The CSV output could be better, but it turns out by having the CSV and the JSON data, we can easily post-process with Python and pandas, and it's actually quite fast. We could use Adios or HDF5 or SQLite if you had a different application need, for example. We could potentially stream this data out to Mochi or LDMS or some other service. We've actually worked with some students to implement a simple monitor, which basically just sets up using ZeroMQ and Python, a little tree of data aggregators. And so we can do runtime monitoring of an application while it's executing. We can also pass the measurements from ZeroSum on to other tools. So for example, there's an integration path for tools like Tau or Apex or SCORE-P to also get the same measurements that ZeroSum is doing. We don't have any integration for feedback and control, but that's a possibility going forward. And then finally, there's a branch of this code that also has integration with hardware counter data from Liquid. So if you wanted to just get some high-level hardware counter data just to determine stall causes, for example, for a different node, you could do that. And maybe you want to look at cache misses or something very high level that would give you an indication that you needed to do a performance measurement with SCORE-P or some other tool like that. And that concludes my talk, and I'm happy to answer any questions. This is all the various funding agencies who helped pay for this.
Yeah, thank you very much, Kevin, for this interesting talk. Currently, I don't see any questions in the chat, but we are a small group, so if you just want to unmute yourself and potentially like your video, feel free to do that and ask a question. Yeah. Marcus.
I have a question. Can you hear me?
Yes.
Okay. Yes, just barely.
So what are the requirements on your end to collect all the data? So what kind of system software or software needs to be available to install that tool? So can I do this as a regular user on any system, or do I need to have something special? Do I have to ask my admins to install it?
Yeah, so the reason we created this tool was to avoid having to ask the admins to do anything. So out of the box, it doesn't require anything other than CMake and a compiler. But if you want to do the interactive visual display, then you need HWLoc to get the hardware tree. But that could be easily handled with the Git submodule, pulling that in. We just haven't done that. Maybe I have, I don't remember. Typically for the GPU monitoring software, those libraries are usually installed on the system already. So a system with NVIDIA GPUs would have NVIDIA NVML, and the same for AMD. The SYCL API calls that we're using are just, most of them are generic SYCL calls. Some of them are Intel specific, but that's for the Ponte Vecchio architecture, which is a little bit unusual to begin with. So, but it also works with, so for example, if we tried it on the Polaris system at Argonne, or I'm sorry, at Argonne National Lab to do SYCL measurement on NVIDIA hardware, and that also was we were able to do GPU monitoring with that, so that should work.
Okay. And maybe a follow-up. So you say that you're writing CSV data from all of the ranks in the end. So, I mean, it's only a sample every second, so it should be fairly okay. But what kind of data sizes are we talking about? So do you have some formula to roughly estimate how much data it would generate, let's say, for a 10-minute run on 1,000 cores?
Yeah, so the example that I showed with XGC, it was generating about 27K of data per second. And that application ran for about 12 minutes. So I don't have any back of the envelope idea, but certainly it would be good to model that and determine how much data are we generating, because for some of the metrics, so for example, the GPU, maybe you don't need the GPU data, or maybe you don't need, it would be nice to be able to turn things on and off and control how frequently you're collecting data or how much data you're collecting other than just the frequency. So no, we don't have a formula for that yet, but it's a few megabytes once you're dealing with dozens of nodes. I can see it being quite a lot of data in the long run. And the way that it works now is it doesn't write the data out until the end of execution. And so that's why we were looking into various streaming solutions for getting the data out. Something like Adios, where you could just write it to memory and it's gone. And then Adios can either, if someone's listening or not, the data will just be transient in that case.
Okay, so at the moment you're just writing it out immediately after the data is collected.
Yep.
Yeah. Okay. Got it.
Yep. Mm-hmm. And Laura had a question in the chat about, did I understand it correctly? It's a Python script to add the job script with any. No, it's not a Python script. It's a bash script. And you just stick it in between your S run or MPI run or a JS run command and your executable name. I assume, does Scalaska or Scorpy have something similar to that? I assume. Yeah. And so it's just a bash script that goes in between. Yeah. Looks like you get it. Okay. Piero,
hello, can you hear me?
Yes.
Yeah, yeah, very interesting talk. No, I'm curious about your cited the computational steering, facility with this tool. So I heard this. Yeah, unfortunately, I'm sufficiently old. Many years ago. So it's still a research topic in high performance computing, or
as far as doing computational steering?
Yeah, computational steering.
So we have another tool that does something similar, but not with this data. So there's a tool called Apex within our research group that was designed for asynchronous tasking runtimes to do some steering for thread schedulers, for networking decisions, and things like that. We're also using it integrated with the Cocos abstraction library, which is used as an abstraction library around GPU programming to help optimize tilings for kernel launches on NVIDIA and AMD hardware. A lot of that's still research work, but it doesn't use any of the data that's going on in this tool. This tool is really just looking at the data from an operating system perspective, and maybe there's a way for an application to determine that it could change the way it's using the hardware or the operating system differently.
Okay, thanks.
Yes, you're welcome.
I also have a question. It's a little bit related to what Marcus said. So how scalable do you think is it? I mean, it's like a really low-level, simple library, so you kind of expect it to like really scalable. But I guess like in the current form, there's no to make sure that we'll use parallel I/O to kind of like collect the output on a really large measurement, and especially I guess your sunburst display will not scale very well.
Right. Yeah. So so each process is maintaining its own CSV file, or it's maintaining its own data set. I could see where if you had a very long running application, that might become a problem, where if you're collecting frequent data. So if you're collecting 26K, 27K once per second for 10 hours, that could be a lot of data, even within a single process space. And if you're scaling out to thousands of processes, you're going to end up writing out thousands of files at the end of execution, which may, so that's another question is assuming you can collect the data, can we even post-process the data? So far, the analysis scripts have been capable of doing it so far. And going up to hundreds of processes, but we haven't tried anything with thousands yet. And we also haven't thought about it as something that's an always-on type tool. I mean, we designed it to be an always-on type tool, but we haven't actually tested it in those situations yet, where if you're running it for very long times. But yeah, these are, I mean, scalability issues are definitely something to deal with going forward.
Yeah, I just like to ask this question because when you look at the top 500, the smallest system on the top 500 has 7,800 cores.
So you say that, but how many applications are actually running more than 256 ranks?
There is applications on like national centers. Yeah, I agree. Yeah.
Yeah, many users are in the hundreds to thousands. type number of ranks.
Yeah,
So,
unfortunately, yeah, which
yeah.
makes for us compute center people harder and harder why we need with like 10 million core systems.
It's
Yeah,
hard to justify.
okay,
Yep.
yeah. Any other questions in the round?
Yeah, sorry, I have a question.
Sure.
Will be maybe you told us already. Sorry if I missed because I was connecting later. But in case I want to compare two executions, so this is the case where for instance, I run today, then I'm gonna run in a month. So I'm collecting again the data. Are you supporting kind of comparison that maybe will tell me yes, now it's gonna get slow because just to say the network is slower?
I don't support that, but there's nothing that would stop because the data is just CSV data. It's very simple format.
Okay,
if you loaded it into a Python script, you could easily do that type of analysis.
That's great. Perfect. Thank you. Yep.
If you're grabbing basically operation system data, do you run into issues when you have a shared node between different users, or is it all basically all identified by a process?
That's a really good question. If you have a shared node scenario, typically the scheduler is going to restrict you to some hardware. And so because we're asking the operating system which hardware is this process assigned to, that's the only hardware we're monitoring. Now there's an option to monitor the entire node, but if you, by default, what we're only looking at is if my process is only allowed to run on the first 4 cores, I'm only going to monitor the first 4 cores, and I'm only going to monitor the processes within my process space. So it should work fine on a shared node type scenario.
Okay.
Maybe
Marcus.
another question about a crazy use case. So what if you would have multiple S runs in a single batch script? So of course I understand that you can add the imposter script to all of those, but would there be a reasonable way to combine that data and say, oh, okay, my entire execution or my entire execution of the batch script had this or that behavior?
So are you thinking of like an NPMD type scenario, or are you thinking
more like a workflow kind of thing? So you're running 2 or 3 parallel executables within the same batch job. But okay, NPMD would be similar, but there you have them parallel to each other, right?
Yeah, so right off the top of my head, I can think that there would be an issue because the CSV files are named a generic name plus an MPI rank, and that's it. Okay. So you would probably need, we'd have to make some code modifications to support running multiple different MPI applications at the same time so that you would have unique output files and unique logging for each process. But then at the end, the post-processing should be similar. You should be able to combine it all together.
Okay.
It should work with either MPI or SRun, yes.
Okay. Any more questions? Okay, then again, thanks you very much, Kevin, for this interesting talk. Thanks everyone for joining. We will have more pop webinars coming up in the future. Follow us on our social media channels or subscribe to our newsletter to learn about it. So thanks everyone. Have a good weekend and goodbye.
Thanks again. Have a nice weekend.